Hi, Ed.
Hey there, Jim. Here we are again. Okay.
Yes, indeed.
Mm,
Hi, all.
Hi, Bob.
Hey, Bob.
Ships passing by. As for us, we keep searching and finding. Did we ever hear whether that guy was going to join us and help explain some of the stuff?
He said that he would. Paul McCudden?
Yeah, Paul.
Yeah, he said he could make it. I sent him the link.
Okay.
I see we got some information from Jessica Draper,
Mm-hmm.
some PowerPoints. I started flipping through those, but I haven't gotten through them yet.
Yeah. Yeah, I looked through them and it's actually got quite a bit of information in there. And I've actually used some of it. But uh, thinking about backing up and doing some of I'm trying to think the other guy up there with Russ, not using his program and using Speckle Tool Box in that slow way. See what difference that it makes on some stuff.
Hmm.
I'm still not convinced that the G2P that we're working on is have it right.
Which one?
It's the 401 one.
Oh, that's an important one to me.
Yeah, yeah, I've done the others, and but that's actually an important one because that's the one that sort of is a problem child too.
Yeah, right.
So that's been concentrating on that.
That's great.
And Gary and them were worrying about the Form sixes, and I told him, I said, those are really just for us figuring out the resolution of our telescope, helping us find
Yeah,
that.
yeah. We need to kind of all get on the same page there on those because Jim is working uh, 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 10140, that star, that was the problem child, and I'm working the 12316, also has a problem orbit as the first two papers. So those are kind of the most important to focus on. I think immediately that and the calibration stars. And then the rest of them we can kind of work following those, I thought.
The only problem child I've worked on is the 10140. So,
Greetings, gentlemen,
Hi, Gary.
Hey,
hey,
Gary.
Gary. Greetings.
and salutations.
Yeah. We are expecting that Paul McCudden will join us to talk about orbits and how to get those. It'll be good for us to be able to draw them because we ought to be including them in our paper. And it would be better to use that program than to use a protractor and try to cut and paste a data point on the orbits that we've got. So hopefully
Been working on the orbits thing. I sort of figured it out, but probably
Have you
not
tried?
correctly. Yeah,
Have you
Yeah.
tried importing the history?
yeah.
Did it work?
Actually, it does work. And then
Okay.
I tried, redoing the orbit better or refitting the orbit. And I came up with some pretty good orbits and I tried to do it in Desmos and that worked up until a certain point. And then at Desmos, it just went crazy.
Hmm.
So I don't know what I'm doing there that's wrong.
Hmm.
And I'm
It
lagging
wants to,
behind.
yeah, it
Not
wants to
today.
say I'm miscalculating the H and the K, but I'm using what they said to use, so I don't know. And, hey, Ross.
Greetings.
Yeah, I haven't heard anything back from the college,
Yeah, me neither.
so
Russ sent a plea to Veronica, who I think helped us last time,
Yeah.
but I have not heard back from her or seen anything from her.
hey, Paul.
Russ,
Oh, our
you're
guest
muted.
star.
There we go. Can you hear me?
Yes,
Yes.
Yes.
Good. Hi.
Yes.
I'm on a different computer here. So
yeah, it's inside.
pardon?
Okay.
It's inside. I think last
Yes, I'm
time.
inside. I'm not in the observatory. I just hosted 15 Girl Scouts at the observatory looking at
Oh boy.
sunspots. So
Oh.
Oh, cool.
I'm a little frazzled. But yeah, I'm happy to go over a little bit of the orbits thing or whatever your agenda is or
Yeah. We thought we would start with what you can do to lead us through how to do some orbits.
yeah. Yeah, sure,
Before getting
absolutely.
into the meat of our paper that we're trying to put
Yeah.
together.
Yeah, Russ just says you guys are super organized down there. I'd love to see the team in action. Sounds like a very impressive operation. So
Ooh, I'm not so sure about that.
yeah. Well, all right. Well, let me, if you don't mind, I'll share my screen here.
Yeah, sure.
And okay. All right. Do you guys see Speckle Tool Box there?
Yes.
We see a blank blue screen.
Yeah, that's it. That's it.
Okay.
Okay, so I can't claim to be the expert, but I have done this a number of times now. So, whoops. Oh, okay. All right. So you have data. You took it with. Did you use Speckle Cap or Nina? I'm just curious.
Speckle cap.
Speckle Cap. Great. So you got data. You use Speckle Toolbox to get a position, angle, and separation, and did all the BSP and all that stuff. And now it's time to kind of put it in place along with other historical data. So the way you do that is, and I assume you're using 10.06 Speckle Toolbox?
Yeah.
Yeah.
Yes.
Yeah, so click on orbits and you get the orbits screen. You then click on read observation file. And, oh, I gotta go find one here. Give me a second. Oops. So I'm going to find one from our paper we were working on with my students. Okay, so here's the text files from the USNO. So I think it was 1158. So let me open that one. And boom, there we go. So this is Fortunately, I only have one screen, so I got to drag you folks off to the far right here. But there is the historical data plotted in orbits.
Well, now
It's colored. Oh,
this
go ahead.
was a text file that just had the list of all the
Yeah, let me.
observations.
Yeah, so when you can order, you send an email to the USNO to Rachel Matson and say, I would like the historical data on A, B, C, D, E, whatever your WDS star is. Sorry, I can't think and speak at the same time. So, and then you'll get an email back that has these text files along with a explanatory file explaining what the is in the files. So when you open one of these text files, here's all the historical data for WDS 06549 plus 1158. So every published historical observation, the date, obviously the day of observation, here's the position angle, here's the separation. These, I believe, are uncertainties in those two things. The magnitudes, there's a few other bits of information, the size of the telescope used, the number of nights of observation, and then of the type of observation, there's a whole, you'll get a text file that lists all the codes for the type of observation. MA is micrometer, and then S, for example, is speckle. So things to start with S, there's different kinds of speckle. What did I say? And then the three, and forgot what the last column is here. But, and then there's a reference to down below all the published papers from where that data comes from. So you can go track them down one at a time. So for 1932 was whatever this is, H. Ferner, Greenwich observations, etc. And then if your pair has a published calculated orbit, it'll be down here below in the orbital element section, along with a reference as to where that orbit was published. And these are the traditional orbital elements, okay? And the uncertainties down here, I believe this is, yeah. And so that's the text file. And when you open it up in orbit, it automatically plots all those historical points. They're color coded by type of observation. So you can see SE. Again, if you open up the text file that comes with your historical text file, it tells you what all the different types are. But S, any kind of S is speckle. Any kind of M is micrometer. Why can't I scroll down here? This is weird. I'm not able to scroll down. There should be more down here, more technique codes and observations. You can then, if you uncheck a particular group of type of observation, it will not plot those. It will remove them, which is very useful. So these orbital parameters up here under orbital parameters are taken straight from that text file. So that's whatever was published in the published orbit in the text file. And then down here are a set of values, parameters that set the ellipse on the visual plane. So they're not orbital elements. They're just numbers that tell you the exact shape and size, semi-major, semi-minor axis of the visual ellipse, the ellipse as seen from Earth. Okay. The WRMSD in milliarcseconds is the weighted root mean square deviation of this calculated orbit from the published data. So 172.808. Okay. Now, so that's great. And you could, if I click optimize, so for example, if I remove, I don't know why I can't scroll down, but if I remove the micrometer observations,
Try enlarging your window.
pardon?
Perhaps. Is your window enlarge.
It's as maximum as it gets, I think. Oops, what did I do? Oh no, I crashed it. Okay, let's try it again. Orbits, open, 1158. Weird. Okay, well, let's just say I wanted to remove this CL. I don't remember exactly what technique that is, but let's say I want to re-optimize the orbit, but not use the CL data. Or, for example, I could change the weighting of each of these types. I could say, oh, that CL data is I trust that more, so I'm going to weight that as a 5 instead of a 1. You can choose your weights however you want, but let's just, for now, ignore the CL data. Then if you click optimize, the program will recalculate an orbit, and as you can see, hopefully the WRMSD will go down. In other words, it's a better fit to what data you're using. In this case, it hasn't changed much. So I'm going to click end. But the main thing we do with this, the main use for this, is to add custom observation file. So this is a separate CSV file that contains your observations. So if you click on that, and in our case, where is it here? Here's 06549 plus 1158 new data. I'm going to show you what that file looks like, first of all. Here it is. So when you do a new observation, you have a position, angle, and separation taken on a particular date. You create a simple one-line CSV file that has, let me just stretch this out a little. It's simply one line for each night observation or each average nights of observation that has the date, decimal date, the theta you calculated, measured, the rho you measured, the aperture of your scope. In my case, it's a 14-inch Meade. The reference, you can use any, characters you want. Ours is Bald Observatory 2026. You can put anything you want in there. And then the technique code, we just use S for Speckle. So that file, then that's it. If you did it on, 5 different nights and you wanted to put all 5 different nights in here, you just have 4 more lines. But each line is one night or one average of several nights. And all you then do, I'm not going to say, all you then do is open up that new data. Where is it here? Right here. Open up that CSV file, and it may be hard to see, but your new data has now been added as a point here. Now, sometimes you got to find out where it is. So if you right click, it'll tell you the information on each point. So, there's ours right there. BO 2026 Speckle with theta and rho, aperture diameter, and there it is. It's included with all the other data. So now you can re-optimize or optimize using your additional data point. So I'm going to, well, it doesn't change much, which just tells us that our observation was pretty much on the ellipse that someone else had published. But then, as I said, the important thing and the interesting thing is you can weight different types of observations differently or remove entirely observations. So what my students and I have been doing is we've been re-optimizing using deleting all the micrometer data. So we figured, that's older data, probably less precise. And we mentioned, we say we're re-optimizing using only non-micrometer data. And I think in this case, we got this WRMSD down to like 50 or something. Much better fit to that data. And then, as you can see, when you do that, the orbital parameters change and these apparent ellipse parameters change. And what we've been doing is then taking these apparent ellipse parameters and entering them into our Desmos plotting tool that allows us to plot the original published orbit and our new re-optimized orbit and compare them side by side on the same graph, because it turns out trying to like cut and paste this image from orbits is not easy. It's not really well suited for putting in a paper as a figure. I've asked Dave Rowe to maybe make the background white and but anyway, so that's kind of the nutshell of how it works. We don't publish these orbital parameters. We just publish or show in our paper a visual of the two orbits as plotted in Desmos. And in this case, you can see the re-optimized orbit is not that much different. It's actually reasonably different if I could get rid of the micrometer ones, but for some reason, what if I do this? Wait a minute. No. Can't seem to get down there. Down here at the bottom, there's some micrometer measurements that I can't uncheck for some reason when I'm using Zoom.
Can you resize your image? That's
what I was just doing. I was control minus to try to zoom out, but for some reason, maybe if I stop sharing and do it. Hold on. Let me try it now. Control. No, I think this program that Dave Rowe wrote doesn't work well with some of the Windows things.
You need a bigger monitor.
Yeah, this is just a laptop I'm using here. Sorry. I have, well, anyway. We did this actually, interestingly, for one of our other targets with my students, which was, actually, let me just show you here while we're here. I think it was it 5057? Yeah. So this one, I don't know if you can see. And by the way, you can scroll with the mouse to scroll in or out and all that stuff, drag it around. But this one, the historical observations are essentially all just a line. And we were hoping that our observation would catch it as it maybe turned around and started heading back in this ellipse. And let's see if I've got it here. 5057, new data. Oh, yeah, here it is. I think this is it. Oh, now it popped back out. But our new data is basically, it scrolls the opposite of what you would expect. Our new data is basically, where is it here? Is this it? No. Is this it? Way over here? No. Anyway, one of these is our data, and it basically shows that our data is just continuing in this straight line. So we don't think this is actually an orbit at all. Whoever published this orbit is Malov, I think, was just grasping at straws. I think these are just two co-moving stars. Oops, sorry, my light's motion sensor here. Sorry. So anyway, yeah, it's really neat. It does a lot of stuff. Now, what is actually under the hood and how he calculates the optimization, that's for Dave Rowe to answer. I don't really know.
Paul, if you could leave your screen up, let me just mention a few more things, okay?
Sure, of course.
Okay, first thing is that I sent you all the file, so you'll probably end up wanting to ask one from Rachel Matz, and just a single email, ask her for the files on all the known orbits. In fact, all the WDS stars too, to get all the information to update. Because the file I sent you it's a couple years old. Pat Boyce got it off of Rachel Matz on essentially all the grade 1 through 5 with known orbits. So you can use that directly. The second thing is, one thing we found useful is if you have a few stars like the one the Paul first showed, there was one that was way off there. You can click on it, but click on the one up there that's a ways off.
This one over, this one over here.
Yeah. So if you show that, it'll tell you how many the standard deviation of it's off.
Yeah, distance
Mm.
38.7. I don't know if it has
Yeah, and
that information.
when you can compare that, what I do is you can compare the distance with your weighted reach.
Yeah,
Yeah. So at any rate, there's a way, and I can send you a paper that explains it. And so you can delete the outliers.
right. So if
So
you
if
just,
they're more than 2 sigma or 3 sigmas, whatever you decide. Yeah, when you click on that, show how you can delete
yeah,
it.
so if you right click, don't use an optimizer, then it
Mhm.
will not use that one.
Yeah.
And it puts a
So,
little circle around it to indicate that you decided to ignore that when you
mm,
re-optimize.
So then the third thing is go down over on the left where it's a semi-major axis, semi-minor axis. Okay, those are the two values that if you put those in directly into Desmos, it won't work. It'll give you something weird. Those need a little bit of a trig transfer
Yeah,
because Dave used a little different. It's when you rotate the thing. So when
yeah,
you're doing the trig transfer, I actually spent several hours doing refreshing my memory on simultaneous trig equations and their solutions.
yeah. And Russ wrote a nice little paper that explains how to take these numbers, the angle, the X and Y center coordinates, the semi-major and semi-minor axis, the eccentricity and the rotation, and put those into this Desmos template we have, and then boom, it'll exactly reproduce that orbital graph.
And they all go in directly except for two of them, and two of them just need to do a simple trig
Yeah,
conversion.
it's like X times cosine theta minus Y times sine theta. Anyway, it's in this nice paper that Russ wrote.
And another thing is on weights, you can, we would typically, often leave, well, if there's if the orbit kind of closes in on itself, and so you have good speckle observations all the way around, and then there's a bunch of micrometer ones that are just way off, then in no sense use them, and then that's actually what Andre Tokovinin recommends. However, on these slowly moving ones, there'll be a bunch of micrometer observations, and only recently a few speckle. And so if you throw all the past micrometer ones, and they may be actually the ones really showing the curve. You can't do that, but you can give the speckle higher weight. So maybe you leave the micrometer at 1 and put your speckle at 10 or more. So you can play around a little bit with that. And there's uh, so one of the things we got involved in was just playing around with this, saying, well, is there a scientific way to assign the weights? And the answer is yes. You can, what you can do is you can do a plot. Uh, so you get the orbit, and then you plot just the micrometer ones, and they'll come up with some mean value off, some off of the orbit, and you plot the speckle ones, and they'll do the same thing. And then based on the number of them and their mean uh, average off their mean root mean square off the plot, you can scale your weighting factors. So it's essentially scaling it according to the information, the content, how bad the error is.
Yeah, I should say I have not done that yet. So
Yeah, and it's kind of fancy, and it's often unnecessary. And the last thing I want to mention is that, so if you do find it way off, your new orbit is significantly different, because you add your observations. Oh, and often there'll be observations on the spreadsheet, on the text file that you get from the Naval Observatory, past the date that you see up in the upper right-hand corner when the plot was the orbital elements were derived. So what's happening is some like let's say Bill Hardkoff in 2009 publishes this paper with the orbit in it, and then after that, let's say Andrei Tokovinin takes a hack at it for a couple of times with a SOAR telescope, really accurate. And those, so U.S. Naval Orbiter, they'll pick those up. They'll include that in the spreadsheet, the text file that you get from WDS. But those new points aren't on the plot that the Naval Orbits Observatory had.
Right.
But when you insert this in Dave's program, they will be on the plot, and they can show up as being way off, and maybe your observation agrees with them. So then, when you get a new orbit, you really want to let the astronomical community know that you've got a better orbit. So when you do your weights, you're all finished with everything, you throw away the outliers and so forth, and have a new orbit, then and Paul, show the orbital elements in the upper left-hand corner.
Okay, so whoops.
Yeah, so those will now be different, and those are the ones that you publish. You
Right.
publish those, and this means that the Naval Observatory will then, at some point, they'll stop doing this, but at any rate, what they've always done in the past is they'll eventually come up with a new plot, and up in the right-hand corner will be reference your paper, and the first three things, the code of it is going to be a code assigned to the first author of that paper.
Right. So I think what I was saying, for example, whoever published this orbit did it in 2020. But look, here's an observation from 2022. So that was obviously not included in that published orbit. Excuse me. So revising the orbit would include this point. Oops. So
why would the orbit not have been revised with the most
Well-
recent observation?
because no
Because
one bothered to calculate it and publish a paper with the revision.
Okay, they
Yeah.
published the observation, but did not emphasize that this was a new orbit.
Well, no, it's a case of the U.S. Naval Observatory. They just kind of, if the new observations published, they add it to their database. Someone publishes a new orbit, they put it in their database, and so it's very common. In fact, more often than not, the published orbit doesn't include observations since the published orbit, because there's astronomers out there, they'll just make new observations, and it's kind of an unwritten rule that, unless, you can go through and start just without making any observations yourself, look for ones that need new orbits and calculate a new orbit and publish it. But that's kind of frowned on, that's a little bit data mining, it's more, and if it's just slightly different, that's kind of, that's not, but if it's changed significantly, or there's a number of new observations and you've added the most recent one, then yeah, it's fair game to publish an orbit. But there's no actual written rules. It's just kind of what they kind of generally do.
Yeah, so for example, this 2022 orbit is by Rachel Matson, and it says, in preparation. So maybe she's writing a paper right now that will calculate a new orbit and will replace these values. But until that case, the 2020 orbit published by FMR 2020 is Rica Romero.
Oh, I know Rico. He's a very advanced amateur in Spain.
Yeah. But in this case, there's only, looks like one new data point, and of course, our own in this case, two. So that's two new data points to possibly recalculate the orbit. But I don't know if that's enough to say we've definitively found a better orbit. But certainly we can at least say that the orbit probably should be revisited.
Yeah, and what you can do if you think it's a not a binary star, you can just do a linear fit to the data. And I think they still have, they have a they publish and plots of what they call rectilinear elements. And so these are double stars passing each other in the night.
Yeah. Or traveling together with each other in the night.
Yeah, that's right. They can be common proper motion pairs.
Right.
Well, now,
So
how would you indicate a rectilinear plot?
I'm not 100% sure, but I guess if you had, for example, whoops, this is the other. Oh yeah, so here's that plot, and if you just take this data and fit a line to it or fit a polynomial to it and see how close
Yeah,
it is
well,
to
it'd be a
the
line through it.
fit a straight line.
Yep.
Yeah, I guess I have not done that. We've not. This is the first one my students and I have found where it appears to be just a linear relationship. It's not really an orbit, even though it's
Yeah,
been published.
we've done it in the past, and it went into their rectilinear catalog. And so if you look up rectilinear elements, and you can see if they still have that catalog. But even if they don't, you could just calculate them. So it's essentially it's just changing RA and DEC as a function of time. Well, or to put it the other way, yeah. So it's just changing position, east and north as a function of time.
Well, so anyway, so that's kind of the summary of my understanding of orbits and how we can use it. So, yeah.
But to then do this examination justice, we need to go to Desmos to be able to bring it into our paper.
Yeah, well, I guess I guess if you're a Python wizard and you can do the same thing Desmos does, plot these ellipses, but I'm not a Python wizard, so I use Desmos. So
now you said our Desmos template, yes.
Yes. I can track it down and send a link to it, and it's basically, oh gosh, let me just see. I am going to have to run in a few minutes, but let me see if I can find it here. I don't know where my browser went to.
Is because as I went into Desmos, it was a very much blank slate. It looked like,
oh yeah.
I'm staring at an Excel spreadsheet. I'm like, what?
Yeah, no, you have to have the template with everything. Here, let me show you an example here. Hold on, I gotta drag.
And I think I have a template that goes with the paper explaining the whole thing that I might be able to find and send to you too.
Here, I have it right here. Let's see, share.
Oh, good.
Screen. Okay, so here's my Desmos account, and here's a bunch of orbits that I've plotted. So, for example, here's one. I think this is the one I just showed you, 2757. Anyway, in the left-hand side, there are these entries, this H1, K1, A1, B1, and Q1 are those numbers with slight corrections on H1 and K1, as Russ mentioned, that you get from orbits. Put the values in here. You have to calculate H1 and K1 according to that paper that Russ wrote, and then it'll plot this orange dot. See if there's a plot of that orbit. And then below that are actual observations from the historical record we just put in manually. or in this case, I think we used a table. And then we added to them, where's ours? Yeah, BO. Oh, this is from our other paper, but anyway, we labeled it BOCCD 2025. So this is our two new observations of this particular pair. And you can change, the color and the symbol. But the main neat thing is to add this plot, this little section that plots the ellipse, either as measured from the historical data or as remeasured from orbits.
Okay, so you put in those orbital elements and it drew the orange line.
Yeah, it drew the orange line. We put in H1, K1, A1, B1, and Q1. Q1 is the angle. Here, let's show you. Q1 is the angle theta, in this case 102.49. This is a different example, but theta is what we call Q1. B1 is the semi-minor axis, in this case 0.061. A1 is a semi-major axis, in this case 1.128. And then H1 and K1 are calculated from a combination of this X, this Y, and then the sine and or cosine of theta. And it's just a simple, it's like X cosine theta minus Y sine theta. Russ, do you remember? I don't remember off the top of my head.
I don't remember, but that was fun. Like, refreshing my simultaneous trig equations.
And here's the actual
But that's
equation.
important to know that you just can't copy the value.
Yeah, you
Actually have to
copy
transform it.
some of them, and the other ones you have to calculate. Here's the actual equation of the ellipse. It's plotting. But you would, of course, not touch that. You would just change the parameters.
Mm-hmm.
And then if you wanted to copy and paste this whole section, you could add a second ellipse for the reoptimized parameter values. In this case, this is an old one, so we just have one ellipse. And then the fun part is you can change the symbol for types of observations. So I think I have a table down here. Oh. Yeah.
And this table you entered manually though to put the points then.
Yes.
On the,
now there's a
graph.
way of taking the historical data file and just copying this into an Excel spreadsheet and then cutting and pasting it into this table in Desmos. But I've forgotten exactly how to do it. So if you have, 250 historical observations, you're better off turning this into an Excel spreadsheet, stripping out everything except the theta and rho, and then there's some weird thing you have to do with adding an extra column and then cutting and pasting. I don't remember. One of my students knows how to do it.
So I've done it in the past. I'm not sure I would remember, but
yeah. But then, for example, you could. Yeah.
Those are more or less put in a manual mode.
Yeah.
Yeah. There's another way that's lots easier. Instead of putting these in, you can take the U.S. Naval Observatory plot that you get from the Naval Observatory that that we were looking at, that actual plot, and you can put it in as the background to Desmos.
Yeah.
And
as I did here, see. And then you can kind of fiddle with the parameters, until the two coincide.
And to do that, you just have to rotate the Naval Observatory plot by 90 degrees to get the x-axis to be the same, and then you have to scale it. And there's ways to calculate the scaling factor, or you can just do it iteratively. And that's in that paper that I sent you that Michael Ellis and I did.
Yeah, there's the trial and error method of lining up these two. And then there's the orbits parameter method. But in either case, you should end up with the Desmos ellipse right on top of the sixth orbit image of the orbit. Something like that.
And it's possible to get it very exact matchup too. You can get it so you can hugely magnify and see that they're still
Yeah,
very lined up.
but it's really meant as a visual aid anyway, so I'm not sure the super accuracy is that important, but
Well, they'll coincide if you haven't determined something has gone seriously awry with the orbits. Okay.
yeah.
Assuming that you've got an observation that is in line with the previous orbits, you're confirming the old orbit is pretty good then.
Yeah.
And typically, and if it isn't, well, typically you might want to show both. If you calculate a new orbit, you show, in different symbols and colors, the old orbit and the new orbit, and so the reader can judge, how it differs. So,
Yeah, we do one in dashes and one in dots or something.
So it's not just a matter of your new added observations, it can also often be someone else's added observations since the orbit was last calculated and plotted.
Mm-hmm. I'm going to have to run in a moment. So, any other?
You mentioned there's a template. Does the template make it easier to enter everything in so we would have to do it manually?
Yeah, well, as I say, there's a way of taking the USNO text file here, transferring it into an Excel spreadsheet,
Oh, okay.
and then importing that Excel spreadsheet into a table here. But what I've found is that it's easier or it's better if you take all of the measurements of a particular type and import them into separate tables. So you can have different symbols for the different types of measurement. So you kind of have to
types, a micrometer.
So in this case, I might put all the micrometer ones in one Excel spreadsheet and bring that into one table in Desmos. And then D, I think, is CCD. So these three CCD measurements into a separate table, and then these two speckle measurements into a third table, or a three speckle. And then this HH, I think, is Hipparcos. So that would be a separate single entry table.
Yeah. But if you use the U.S. Naval Observatory plot as the scaled background, then, for a published paper, you don't have to enter any of these into Desmos. The only thing you have to enter into Desmos is observations that were made since the plot was published and your own observation. And so that's the one thing we often do. And so it saves you the effort of having to even worry about all the other ones.
Okay, I'm sorry to do this, but I have to run. So
Thanks, Paul.
Yeah,
really appreciate it.
Thank you, Paul.
yeah, I'm curious to
Thanks
see what
very much.
results you get, and best of luck.
Okay.
Thank you.
All right, take care.
So who are we supposed to send the email to, the U.S. Naval Observatory, to ask for the data?
Dr. Rachel Matson. And if you